Hello and welcome. We are Team XMOS. We are here to present to you the Smart Baby Monitor. Our project is led and directed by Dr. Andrew Kavanaugh, a URI alum in electrical engineering from the class of 2008, Stephen Enzovino, a URI alum in computer engineering from the class of 2021, and Kieran Thacker as a consulting technical director from the class of 2022. Dr. Andrew Kavanaugh also went on to get his PhD in electrical engineering from WPI, and Kieran Thacker is currently enrolled as a master's student in quantum computing at the University of Rhode Island. Our team is comprised of 2 electrical engineers from the class of 2022, myself, Nathan Dwyer, and Dow Townsvath. In addition to studying electrical engineering, we both have a minor in mathematics. To give a brief overview of XMOS as a company, they're the home of multi-core microcontrollers, with an HQ in Bristol, UK, offices in the United States and Asia, with a high focus on the artificial intelligence of things, consumer and professional audio, industrial robotics, and they are the developers of the XCORE.AI architecture, a key feature in this project. A project which has its roots and motivations in the marketplace for AIoT devices. The majority of AIoT devices are internet connected. They lean on things like cloud services and off-site artificial intelligence to achieve their features. However, using the XCORE.AI architecture as well as the very well-established XMOS voice front end, we can do all of these things in one singular package. The package that we're going to do it in is in a baby monitor, something that parents can agree needs a lot of privacy. Now for our project, our anticipated best outcome is to develop a custom daughter board that can interface with existing XMOS development kits. It'll have capabilities like AI echo cancellation, speaker connections as an output, communications with a remote unit, and hopefully, time permitting, sound recognition and event detection for both units. These units will of course not have to lean on anything internet connected, will not require an internet connection, and will talk to each other hopefully through radio communication by the end. On the road to our best anticipated outcome, we have some key accomplishments from the hardware section. First of all, we are excited to announce the fabrication of our first daughter board prototype, designated the Baby Komodo, using an all-new buck converter from Texas Instruments, as well as a new low-power voice codec from CML Microcircuits from the previous year. We have also now received an evaluation kit of that microcontroller from CML Microcircuits that we hope to interface directly with the development boards to give us a better oversight of its capabilities. And speaking of integrations, we have our key accomplishments for the software, which involves testing the XMOS development board, specifically the Explorer board provided to us, and messing with and merging different XMOS examples to create different programs that have functionalities such as the microphone and data streaming at once, a key feature for our project. Now looking to the future, the economic impact of our project will be able to create a competitor for current smart baby monitors that combines multiple devices utilities, not to mention doing all of it without relying on network connection, giving unparalleled privacy. This will hopefully establish XMOS as a landmark company in the world of privacy-minded AIoT devices and make them a household name when parents are concerned about their data. Now let's take a look at the whole project with the project block diagram. In the center, we have our daughter board. On board, we have our audio codec connected to our digital audio converter. The codec will provide automatic echo cancellation so that when we play white noise through it, the white noise won't be filtered back to the parent unit and all it will hear is the audio picked up by the microphones. Speaking of the microphones, instead of sourcing our own microphones, we'll be using the Osprey board from XMOS, which will have its own microphones on board. Both will be powered through a USB connection, and on board the Osprey we will have our neural network with our sound event detection software, time permitting. To speak more on my own technical contributions to the project, despite my electrical engineering major, my role was primarily as a computer engineer. I spent my time writing and debugging code for the XMOS hardware, as well as learning XMOS program-specific tools and machine learning software, such as those seen to the right. I also had some minor roles in assisting ELE duties, such as advising on component selection, assisting in the PCB routing, fabrication, and component testing. To be more specific, I spent an extensive amount of time researching machine learning through the Google Machine Learning Crash Course. I then tested a bunch of different sound detection models and ended up choosing a LSTM or long short-term memory model for the project, as that seems to be what everyone uses for sound event detection. In addition, I tested the features of the XMOS dev kits through their examples, such as the internet throughput test, audio and microphone test, and the I2C and SPI test, all things important for the project in the future. But there's still a long road ahead of us. For my future technical contributions, I look forward to interfacing with the daughter board that we've created over XCORE.AI and SPI protocols, as well as implementing the machine learning model that I've picked out for sound event detection. I also need to research and use TCP to talk between two XMOS development boards, which goes hand in hand with porting the existing software that I have built for the Explorer board onto the smaller Osprey development kits, a challenge given their lower cache sizes. Now I'm excited to introduce my partner, Dow Townsavath.
Hello, my name is Dao, and I'll be presenting the hardware portion of this project. At the start of the semester, as a team, we evaluated the previous schematics that was made last year and decided which parts of the board need to be redesigned. So first, we decided that we need to replace the buck converter because it was not outputting the proper amount of voltage that was needed for the rest of the board. I went through a bunch of different buck converters and narrowed it down to a Texas Instrument one that fit the previous buck converter specifications. After designing a new schematic and PCB layout, we decided that it was time to begin prototyping to avoid any problems that we might come across in the future. In the biomedical engineering lab, we had the Volterra V1 machine print out 2 test boards for us for free before we sent the designs out to any other manufacturer. However, as shown in Figure 5, we were unable to achieve our desired results. In the first half of our PCB, it worked as intended because we had multiple indicator LEDs. However, due to the very small gaps in between each pin for the buck converter, the machine was unable to space each track properly, causing the pins to short. Shortly after we discovered our problems with the prototype power supply boards, we discovered another major problem. The previously chosen audio codec was no longer being manufactured. During a team discussion shortly after, we went through different types of codecs, similar to how we did with the buck converter, and chose one from CML microcircuits. When designing the new schematic for the audio codec, I used the datasheet's recommended external components, added more indicator LEDs, as well as taking some features from the previous design. Then after, I merged the 2 designs that I had made. As shown in Figure 6, the leftmost part being the power supply with the buck converter, and everything else to the right of it being the audio codecs parts. After team discussion and approved designs, we ordered 3 boards from the manufacturer Oshpark so we can begin official testing. For my future technical accomplishments before April 15th, 2022, I would like to test the evaluation kit for the audio codec that we ordered to verify that everything works as intended. Also, considering that we shipped our boards out to manufacturers, I would also like to test the PCB to make sure all of our outputs are functioning properly. And after we have that working, we discussed as an extended ABO that we would like to convert the board that I designed into a smaller form factor 4-layer board. As a group, we have key future technical accomplishments that we would like to meet for our ABO. On the hardware side, we want to verify that the new PCB works as intended. So we want our power supply to be working properly and our I2C inputs for the audio codec to be working properly. Also, after that works, we would like to design that 4-layer board to reduce its size. On the software side of things, we would like to interface the XMOS dev kit with the daughter board, as well as implementing machine learning models for sound event detection. The team would like to thank Dr. Sunak for giving us the opportunity to work with XMOS. We would also like to thank our technical directors, Andrew and Stephen, for giving us advice and helping guide us for this project. And we would also like to thank Karen Thacker, a consulting technical director, which worked on this project last year, which also guided us when we needed help. And we'd also like to thank Mike Smith, Professor Jung, and Joseph Reyes for supporting us whenever we had questions about any circuits or PCB making.